Okay, Advanced Placement Chemistry. This is the Day 42, Lesson 22 Calorimetry assignment, and this is the second part of the answers to that. I've had some real problems over the last couple of days doing recording, some issues with my computer, so things are behind. I apologize for that. I will have the rest of the assignments up later on. All right, so we're going to start with, we're going to do number 3. And that is the same as one that's in the notes. So this problem's in the notes, but I want to be able to explain it to you in some detail, and then you can do the next problem, which is identical to it, except the numbers are different. All right. So, dissolving 6 grams of calcium chloride in 300 milliliters of water causes the temperature of the solution to increase 3.43 degrees centigrade. Assuming the specific heat of the solution is 4.18 joules per gram centigrade, and assuming the calorimeter absorbs no significant amount of heat, determine the delta H, change in enthalpy, for the reaction. So there's the reaction, and there's a conversion that we're going to need here in just a minute. So let's go through and pick this apart. All right, so you have 6 grams of calcium chloride. So all the energy that's going to be generated is going to come from the dissolution, meaning it's dissolving, of this in water. Water is going to pull it apart. And we're going to use 300 milliliters of water. So the first thing that comes up is that for the formula we're going to use, we don't need a volume of water, we need the mass of the water. And for water, the density of water is 1 gram per milliliter. Milliliters is a measure of volume, how much space something takes up. Grams is a measure of mass. So we need this in mass. So what we can do is we use this as a conversion factor, and it's going to be 300 milliliters and then we use this conversion factor. So for every 1 gram of water, there's 1 milliliter of water. That's true only for water, that relationship. So that means I put 3 milliliters. It should have been 300. So that means we have 300 grams of water. If it were not water, then we would have to have some density. We saw a couple of problems earlier in an earlier assignment where they gave you a density in grams per milliliter. They would have to tell you what the density of that substance or that solution is. But for water, it's 1-to-1, so it's just a straight up conversion. All right. That causes the temperature of the solution to increase by 3.43 degrees centigrade. Now, usually we're working in Kelvin for temperature. When you're talking about a temperature change, this is a change in temperature of 3.43 degrees, then it doesn't matter which scale you use, because 1 degree on the centigrade scale is the same as 1 degree on the Kelvin scale. So for example, water on the centigrade scale, water is freezing at 0 degrees and it's boiling at 100 degrees. That's a 100-degree difference between freezing and boiling. On the Kelvin scale, water is freezing at 273 degrees and boiling at 373 degrees. That's also a 100-degree difference. So 1 degree on the Kelvin scale and 1 degree on the centigrade scale are the same. The only thing that differs between the two is what they decide to call 0. The point is, when we're dealing with the temperature change, 3.43 degrees centigrade, a change in temperature of that much, is going to also be 3.43 degrees Kelvin. So it doesn't matter which scale. You don't have to make the conversion. By contrast, when we're using gas laws and we have to have a temperature, if it's 0 degrees centigrade, that's not going to work in the ideal gas law. You're going to have to convert that to Kelvin, which is, if it's 0 degrees centigrade, it's 273 Kelvin. You have to make that conversion. But here we don't have to make the conversion. The only thing important is the number, the change. Okay, it says, assuming the specific heat of the solution is 4.18 joules per gram centigrade. This is the specific heat of water, but they're talking about the specific heat of the solution. The specific heat of calcium chloride is something other than this. It's different than this. However, there's so little calcium chloride compared to the amount of water. In other words, 99.9% of this solution is water. that you can just go ahead and use the specific heat of water. You don't have to worry about what it is for this. So we're just going to say that the specific heat of water is going to be the specific heat of the solution, which is the mixture of water and calcium chloride. Okay, so that's just what's called a simplifying assumption. So you don't have to sweat the little bit of specific heat change that would be caused by the calcium chloride. And then it says, assuming the calorimeter absorbs no significant amount of heat. Let's go ahead and make a quick diagram of this. So this is a styrofoam cup. Okay. And what's going to happen is this is water here. And you're going to go ahead and drop this calcium chloride in, and it's going to dissolve, just like salt dissolving in water. And that's going to happen everywhere in the solution here. It's going to take place where the calcium and the chloride ions break apart into ions, and that releases energy when all that happens. Now, just for the sake of simplicity, though, we're going to go ahead and just put the calcium chloride in a little bubble here. It's not really a chamber or a container in here. I'm just kind of putting it all in one place, just to illustrate. But really, it's spread out all throughout the solution. All right, and then we also have our thermometer coming down. That's the thermometer right there. Okay, and this is a styrofoam cup, not very heavy duty. So the characteristic of coffee cup calorimetry is it's a relatively low heat coming out of the reaction. So a styrofoam cup can easily contain the amount of heat. And what else the styrofoam cup does is it insulates. So this is an insulator. That means that no heat comes in or out. Okay, no heat will come in or out of this cup. All right. So what they're saying is the amount of heat released is relatively small. The cup is not going to absorb any of that. Only thing that's going to absorb it are two things. It's the solution. Okay? And that solution is the surroundings. All right? So let's go ahead and define that. So first, what is the system here? The system is what we're studying, what we're trying to learn about. Okay, so the system is the reaction. It's not the calcium chloride, it's not the water, it's no location in here. It's the bonds, it's the breaking of the bonds. It's that reaction which dissolves calcium chloride into calcium cations and chloride anions after the bonds are broken. So that's the system we're studying. It's those chemical bonds and how much energy is in those chemical bonds. Now the surroundings. Okay, so the surroundings is where is that heat going to go, and where it's going to go is it's going to go into the solution, which is the water, those dissolved calcium ions, and the dissolved chlorine ions. We said that none of it is going to go into the cup. That's what the question said. Calorimeter absorbs no significant amount of heat. So all the heat is going to go into the water, the Ca, and the Cl. All right, so that's the surroundings. And by the way, this is not significant to the problem, but just to reinforce it, these two put together are the universe. So we don't really literally mean the entire physical universe. We're talking about this little world right here. The universe is the system and the surroundings together. It's just referred to as the universe. Okay, so now we're ready to kind of state a principle. We're interested in the heat coming out. Why do we want to know the heat coming out of this? Because the heat is the only type of energy that's released by this chemical reaction. And we're interested in the energy that's in those bonds. And since all of it is going to be transferred into heat energy, if we can measure the heat energy coming out of this reaction, then we'll know how much energy is in those chemical bonds. So we have a principle here. When heat comes out of something, it's negative, okay? And that's the way I make a Q, so kind of get used to that. And we use a subscript. So negative heat from the system, the heat is going to be coming out of the system, out of the chemical bonds. that is going to be the same as the amount of heat that goes into the surroundings there, but the opposite sign. So the numeric value of Q here and here are the same number, but one's negative because it's exiting, it's exothermic, and going into the surroundings, which is endothermic for the surroundings, okay? So now what we're going to do is figure out how much heat is going into the surroundings. So we have a formula. And I'm going to abbreviate surroundings here. Okay, so it's the formula that relates heat and temperature. So let's understand what each of these are. Mass. Mass is the total mass of the solution. So we said up here that we have 6 grams of calcium chloride, and we calculated that we have 300 grams of water. So that's going to be 6 So there's 306 grams of the solution. That's the mass of the solution, the water and the calcium chloride together. Okay, so this is going to be all right, this is the specific heat of the solution. And we said we're going to just approximate that by saying it's going to be the same as the specific heat of the water, since the vast majority of the solution is simply water. And finally, we have the delta T up here is 3.43. That's the change in temperature. The temperature went up by 3.43 degrees. And again, it could be either Kelvin or centigrade because change in either of those scales is the same. Okay, so we can cancel our units. Grams cancels with grams, centigrade cancels with centigrade, and the only thing we have left is joules, which is the measure for any kind of energy. All right, so we'll go ahead and do that calculation. And we get 4,387 joules. Okay, and given this relationship that's the heat coming into the surroundings, that's the same exact amount of heat coming out of the system. So we can write this. Okay, so that's the Q coming out of the system, which is also in a constant pressure calorimetry, which this is, coffee cup, is also the delta H, the change in enthalpy. Change in enthalpy and heat are the same for constant pressure. All right, so that's really your answer right there. That's the amount of heat coming out of that chemical reaction. Now, there's oftentimes something else you want to know. You want to know how much heat per gram of the substance are you getting out. All right, so what we have is it's going to be this delta H. That's going to be, let me just write the general formula. It's going to be delta H over the mass in grams. So delta H is this. And now what mass are we talking about? Are we talking about the 306, which was the mass of the solution, or are we talking about the 6 grams that we originally had of calcium chloride? And the answer is we used the 306 because we needed to measure the heat going into the solution to use this formula down here to figure out the delta T. That was the mass for the purposes of figuring out the heat down here. But when we want to know how much energy we're getting per gram, in this case, we want to use the grams of this substance. The calcium chloride is the only thing that's generating that energy. It's not the water. The water's just pulling it apart. But it's actually, the energy is actually coming out of the bonds of calcium chloride. So this is going to be over 6 grams, not 306. And when you do that, you get 731 joules. All right, and that's joules per gram. Now the other thing you might want is how much energy per mole. Okay, so we can just do a molar mass conversion here. First of all, you have to know the molar mass of calcium chloride, and it is 110.98. I did that calculation already. So we take 731 I take that back. Yes, it is. That's correct. And grams here cancels with grams here. That was grams per mole of calcium chloride, and that gives you this. It gives you 81,026 joules per mole of CaCl2. Now another conversion, and that's pretty much everything that you could be asking. By the way, I should have put negative signs. That's exothermic. It's coming out of the system. That's what we're interested in. So this is an answer right here. This is an answer right here if you want it per gram. This is an answer if you want it per mole. Now let's go back to this number here. A lot of times it's expressed in kilojoules. So all you would do is take that number and there is 1 kilojoule for every 1,000 joules. And that's going to equal negative 4.387 kilojoules. I'm simply making that point because oftentimes equals delta H. Okay, that's going back to this original number. It's because oftentimes you express this energy in kilojoules. In fact, you usually do express it in kilojoules. Okay, so that's everything that you could possibly calculate about this particular problem, and that's telling us the energy coming out of that reaction. All right, let's go on now to we're going to go on and do a bomb calorimetry problem right now. Okay, so again, this problem, both the preceding problem and this problem are already in the notes, but I want to give you a full, detailed explanation of how to do them because it's really important you understand calorimetry. So methylhydrazine is a rocket fuel. There's the formula for it, and let's go ahead and figure out the molar mass right now. So C is 12.01, and H6 is 1.01 times 6. And nitrogen is 14.01 times 2. And that gives us 46.09. So I'm just going to write that right away because we're going to need that later on. Okay, so we'll just write that up there. Okay, so there it is. There's the chemical reaction. I'm just going to tell you right now, you don't really need that. So when 4 grams, that's important, of methylhydrazine is combusted in a bomb calorimeter, the temperature of the calorimeter increases from 25 degrees C to 39.5 degrees C. So that's a difference of 14.5 degrees centigrade, which is the same number of degrees it would be in Kelvin, 14.5. So we don't need to make any change into Kelvin for this. Okay, the heat capacity, that's key, of the calorimeter is measured to be 7.794 kilojoules per degree centigrade. Calculate the heat of reaction. It's not asking for enthalpy, so there's some key differences here to pay attention to for this combustion. First of all, let's draw this device. You can just think of it as basically a cylinder. Now it's very heavy duty. It can handle a lot of heat. Whether there's really literally explosion, maybe not, but there is actually a chamber, unlike the last one where we drew the calcium chloride in the middle like this. This actually is a physical chamber. It's inside this little container here. So it's CH6N2 is inside of there, and you're going to light it on fire. Okay, so you need something to do that. So you have a box out here which sends a spark down, and that's called an igniter. It ignites and so we can just draw 2 wires going down there. that are going to ignite this. And then after that takes place, it acts very much like a coffee cup calorimetry. You have heat coming out in all directions. And eventually that heat is going to spread out throughout the water and make the water all the same temperature. So temperature, we need a thermometer here, so there's our thermometer, okay? Alright, so there it is. That's the device. So there actually is a chamber there. There's a bigger container there, and then this is all H2O. It's pure water. It's not a solution like with the coffee cup calorimetry. It's all pure water outside of this. None of the material in this chamber comes out into the water. Only the heat. The heat is the only thing that comes out. Okay, so let's define the system. So this is bomb calorimetry, and it's used for very high temperature, volatile, explosive types of measurements, okay? Things that you can't do in a coffee cup, in a styrofoam coffee cup. Okay, so let's define the system. Okay, the system is the reaction, just like in the last problem, is the reaction that breaks the bonds of methylhydrazine and releases the heat into the surroundings. Okay, what's the surroundings? This time it's different. It's not the water and the solution. It's not the water, it's just the water. The surroundings. So the surroundings is the calorimeter and the water. That calorimeter is this entire physical structure of this device. This container, this little container inside, and the water that's surrounding it. That's defined as the calorimeter. That's simply not going to be the specific heat of water. That's going to be, the calorimeter has its own specific heat. So how do you determine? That's this number right here, 7.794 kilojoules per degree centigrade. That's the heat capacity for the calorimeter. So how do you determine that? It has to be determined experimentally before you do this experiment. If you bought this from a manufacturer, they would list that as a specification, what the heat capacity of this calorimeter is. So that's something you would know from the manufacturer of it. Or you would do an experiment, and we won't get into what that experiment is. That would determine the heat capacity of this calorimeter. The other thing you notice is the term. It's heat capacity. Specific heat is the amount of heat energy in joules that it takes to raise 1 gram of a substance by 1 degree centigrade. But heat capacity takes into account the mass of the substance. So you have to take into account the mass of the calorimeter, and that's done in this number already. That's why it's heat capacity of the calorimeter and not specific heat. If it's a bigger calorimeter with more metal or more whatever is containing it, it's going to have maybe a higher heat capacity, for example. Okay? You don't have to worry about all that. Just understand the distinction here that's made between this number and what we used, 4.18, for water and the solution in the previous problem. Okay, it actually makes the formula a little bit simpler, okay? And again, these two together are the universe. All right, so we have the same relationship, and that is the heat that's going to go into the surroundings. I'm going to just abbreviate that SURR. Is going to be the opposite of the heat coming out of the system. That's out of breaking the bonds of the methylhydrazine, excuse me. Okay, so the same number, the Q is the same on the number, numerically the same, but opposite sign. It's going out of the system, that makes it negative exothermic. It's going into the surroundings, that makes that for the surroundings is positive endothermic. So let's go ahead and write the formula. Okay, there's the formula for bomb calorimetry. Notice it's a little bit different. You don't see the mass. That's because this is the heat capacity of the calorimeter, and we just said it already takes into account the mass of this object and the water. Okay, so that's this. This is the delta T. So that's going to be, we'll come over here, delta T equals 39.5. Okay, and that's 14.5 degrees, whether it's Kelvin or centigrade, doesn't matter. Okay, so let's go ahead and plug in the numbers. Okay, again, this number is that. And this number is that, the change in temperature. All right, so we just go ahead and compute that. Cancel our units. Centigrade cancel. So our units are going to be in kilojoules this time, not joules. All right, and we get 113. And that's what went into the surroundings. So if we use this principle that what went into the surroundings is equal and opposite to what came out of the system, then the Q for the system, it's exothermic, it's going to be a negative number, is negative 113 because the heat came out for the system. And that's the number we're interested in. Okay. So that's essentially the answer, but we're not quite there. There's something else to note. And this is something I didn't talk about any other time earlier, so I'm going to talk about it now. Before we said that Q was the same as delta H, change in enthalpy. That's for a constant pressure calorimetry. That's a coffee cup calorimetry. This is not constant pressure. It's constant volume. Now, you don't need to understand all the details of why this is. You just need to understand what I'm about to tell you. That this is not equal to delta H. It's equal to delta E, the change in internal energy. Okay, it's just a technical distinction. You don't have to understand all the details of why that is. You just have to know that it is. So that's change in internal energy. Okay, there you go. All right, and it's in kilojoules already, so we usually leave energy in kilojoules. Now, if you wanted to know it per gram, per unit mass in grams, and again, the mass that we use is the mass of the substance, 4.0 grams. That's where all the energy is coming from. It's not coming from water. It's not coming from the calorimeter. It's coming specifically from here. So if we want to know how much energy we're getting per gram of that rocket fuel, we're going to divide by the number of grams only of the rocket fuel. And that gives us negative 28.3. Okay, if we want to know delta E per mole of the rocket fuel, which is something else you might be asked, then that's going to equal this and the molar mass. You need the molar mass of the rocket fuel. So we figured that out up here. Oops, I'm off screen, way off screen. We figured that out. That's the molar mass of the rocket fuel, 46.09. So we're going to go ahead and put this here for every mole. Okay, grams cancels with grams. And what we get is 1302 negative. And I'm kind of ignoring sig figs right now. Per mole of the rocket fuel. Okay, so there's all the answers there, right there. And it's delta E. If it's per gram, it's that. And if it's per mole, it's that. Okay. So, let me write down this principle one more time. I think this is an important principle to cover. For coffee cup calorimetry, Q of the system, the heat coming out of the system, equals delta H, change in enthalpy. For bomb calorimetry, the Q of the system equals the change in internal energy. Again, it's not important to understand the details of why those are different. If you take a thermodynamics class in college, you would learn that, but here you don't need to know it at this level. You just need to know when you write the answer, be sure you use this for bomb and this for coffee cup. Okay, let me give you the answers to the other two. I tell you what, I'm just going to put that on the Canvas site. All right, so I'm going to wrap this this video. It's getting long. I'll put the answers up to numbers 4 and 6, the ones that I didn't do for you. They're done exactly the same way. So that's your chance to practice the method and really focus in on the details of what each step is, okay? And you do those two. And that'll do it for the calorimetry lesson, okay? I'm sorry it took so long, just technical issues that have just been plaguing me this week, okay? You are going to have a couple more assignments coming up in the next day, and I'd like to get those done over the weekend because we're going to move on to something else next week, okay? All right, so have a good day, have a good weekend.